Yes, I think we're good. Okay.
Okay, cool.
Yep.
I guess we just make a start then.
Yep.
Give a brief introduction.
Yep.
Hi everyone, welcome to the AVM webinar. It's a great pleasure to have with us today Professor Keith Nelson from MIT. Professor Nelson earned his PhD in physical chemistry from Stanford and then has led the ultrafast spectroscopy group at MIT since 1982. And he's very widely recognized for his pioneering work in ultrafast spectroscopy. But what's quite unusual and exciting for the EPR community is how his team is bringing EPR into the terahertz regime and using the terahertz pulses to directly drive and watch spin transitions in the real time. So it's a fresh way of thinking about magnetic resonance. Please join me in welcoming Professor Keith Nelson. Feel free to make a start when you're ready, please.
Great. All right. Well, it's really a terrific pleasure to be here to get introduced a bit to this community where I'll describe some terahertz spectroscopy just to illustrate some of the methods, and then I'll focus on terahertz EPR, mostly of magnons, but also show some illustrative examples with molecular high spin compounds, and end with a sort of invitation to work with me to extend that to Zeeman EPR and other kinds of applications. So there we go. So I'll start by discussing how we generate our terahertz fields using femtosecond optical pulses. This might be familiar to some of you, but this is a key part of how the terahertz EPR that we're doing works. And in particular, what that will lead to is a variation where there's no free space terahertz field propagation at all. We generate terahertz fields in a nonlinear medium and in the form of a terahertz waveguide, and all of the terahertz generation, propagation, measurement, interaction with the sample, everything takes place there without ever leaving it to go out into free space, and that can facilitate measurements in a lot of ways. So I'll discuss at the beginning how we make the fields at all, and then I'll very briefly discuss different kinds of terahertz field-induced responses. I mainly want to do that to illustrate methodology, just for those of you who don't do this sort of ultrafast spectroscopy. Some of these features may be new to some of you, but I'll be fairly brief in summarizing some work that we do using terahertz fields to drive interesting electronic or lattice vibrational or other sorts of responses. I won't talk about dipoles, but that's molecular rotations in the gas phase. But then I'll go to spins and talk about how we can do terahertz EPR of high spin molecular compounds and magnon modes and collective spin waves. And in the latter case, I'll illustrate how we do nonlinear terahertz EPR, and in particular two-dimensional terahertz EPR, to reveal really interesting features of those sorts of modes. And then finally, I'll discuss what I mentioned before, which is the way we can conduct a lot of this spectroscopy now without any free space terahertz propagation, using a terahertz waveguide-based approach for generation and propagation and interaction with the sample and measurement. Then I'll finish by indicating what some of the current limitations are, in particular various things, mostly involving long time scales, much longer than the time scales we operate on now. And I'll make some suggestions for how to get there, and that would enable other kinds of terahertz EPR spectroscopy using the approach that we do use for terahertz field generation and measurement. Just sort of throw that out there because I'm interested in getting the perspectives of some of you folks who do very different kinds of EPR spectroscopy from what I do, not only because of differences in the frequency range, but also in what the sample types are. In particular, we have done very little molecular EPR, and of course, I would be very interested in doing more, and I'd be interested in getting some perspectives on that. So let me just illustrate terahertz generation, we use it. It's basically nonlinear optics. We use femtosecond optical pulses, and it's essentially an optical rectification process. So our femtosecond pulse duration, it might be on the order of 50 femtoseconds or so. That's very short compared to even a single cycle of a terahertz field. And so what happens is that optical pulse has many cycles, but it has an envelope, the total duration of which is on the order of 50 femtoseconds. And that becomes the terahertz field profile. So there's a rectification of the optical field oscillations to produce the terahertz field. What's really happening, we do this in lithium niobate. There are now a variety of nonlinear crystals that can be used. In the case of lithium niobate, it's actually kind of interesting. What is really happening is the optical field is actually driving strongly polar lattice vibrations. It's rocking that niobium +5 ion is in through stimulated Raman scattering. It's inducing oscillations of that ion, surrounded by a cage of oxygen anions that has a very strong dipole, so it radiates. It couples strongly to terahertz frequency light. And so what we generate, strictly speaking, those are terahertz phonon polaritons. They have a dispersion that's illustrated here. I won't go into that in detail. But the point is that actually inside the medium where we generate these fields, they are admixtures of electromagnetic waves at terahertz frequencies and polar lattice vibrations. That is, what is moving through the crystal, propagating through the crystal, is always a combination of those things. It has a terahertz electromagnetic field, but it also is accompanied by a strong component of that lattice vibrational motion. Because lithium niobate is an electro-optic crystal, those terahertz field oscillations, that electric field changes the optical refractive index, making it quite easy to optically image the terahertz wave as it propagates. And that's what I'll illustrate that here. So here, for example, we took a cylindrically focused line of light and hit a lithium niobate crystal with it. This is very macroscopic. That's about a 3 by 6 millimeter cross section there. And what you see is essentially counter-propagating single cycle waves, very much like what would happen if you did that in a pond of water and launched single cycle ripples, but these waves are moving at light-like speeds, not at sound speeds. And we can build up a stronger field inside the material by not just coming in with a single optical pulse, but subsequent pulses to coherently superpose responses and build up a bigger and bigger response. So in this video, you'll actually see, you can see by eye that the field strength is increasing as it propagates. So here it goes, it's a little fast, but you can see it getting stronger and stronger. Right about now, it's free running. And then if we want, we can couple it out of the crystal and use it for free space terahertz spectroscopy. There are also various ways of enhancing the terahertz field, either the electric or the magnetic field. Here's a simple example where we can locally enhance the terahertz electric field, but they're very similar magnetic field enhancements. It's just a gold dipole antenna deposited on the lithium niobate crystal. You'll see it shortly, I think. There it comes. And you can see by eye that in the micron gap between those gold arms, you can see by eye that that's where the field is brightest. And your little circular structures can also be used to enhance the magnetic field component. It's also really straightforward to do laser machining of these lithium niobate crystals, especially if they're not very thick, and make all sorts of structures, band gap structures, cavities of various sorts, and so forth. So that's what's illustrated here. This is there it is, a terahertz cavity. You can see the terahertz wave reflecting back and forth. What you're seeing on the side of the cavity are just on each side, two trenches of air that have been laser machined right through the 50 micron thick lithium niobate crystal, because the lithium niobate has a very high terahertz refractive index. It's about 5.1. So there's a huge index contrast. So in effect, these couple of layers of air and lithium niobate play the role of a multi-layer reflector. If it were an ordinary optical reflector, of course, there are coatings with many, many layers. but that's because the index contrast isn't nearly as big as this. When the index contrast is enormous like this, the difference between 5.1 and 1 for the air, just a couple of layers already produces a very high reflecting element. Here's a little more of a picture of how we generate strong Terahertz fields in a bulk lithium niobate crystal. The crystal actually is a prism of this sort. It's illustrated here too. And what's happening is, what we're doing is exactly what I illustrated in this video. We're bringing in light, and the light, pumping light, will be here and here and here and here, and it's going to move at the lateral speed of the terahertz wave, so that it's continually building up a stronger coherent terahertz response. And that's what's happening here. Because the refractive index for visible light that we're using to do this pumping, or at 800 nanometers, is much smaller than the terahertz refractive index. It's a little bigger than 2. What happens is, when the terahertz pulse comes in, as it propagates through the crystal and generates the terahertz wave doesn't move purely laterally. It has a forward wave vector component too, very much like Cherenkov radiation, in fact. So the prism is cut so that the terahertz field can leave at normal exit to minimize the reflection. What typically gets generated is basically a single cycle terahertz field, just like the ripple that you saw before. So here's a typical electric field profile. This was calibrated, so this is about 300 kilovolts per centimeter. When we focus this into a sample, or for a measurement, we can get just about a megavolt per centimeter field strength. And this is the Fourier transform. In this case, it's a maximum at about 0.5 terahertz and extends well above 1 terahertz. There's now really quite a wide family of nonlinear crystals that can generate terahertz fields of various sorts, including fields that go to considerably higher terahertz frequencies than this. And that's what's indicated here. These are readily available. Most of these don't involve this kind of generation where we're building up a field as it propagates laterally. They're either phase matched for just generation straight through, or they're very thin, so that there's no mismatch that matters between the speed of the optical light and the terahertz response. Lithium niobate, though, remains quite good for generating terahertz pulses with multi-microjoule energies, and that's still about as good as it gets for pulse energy. It's also straightforward to make multi-cycle terahertz fields. I'll illustrate this again subsequently, but all that was done here was a sequence of optical pulses was used rather than just one, and each pulse basically makes one cycle of the terahertz field, so it's possible to construct multi-cycle fields of all sorts. It's also possible to shape the fields in other ways, right? It's fairly straightforward to make fields that, for example, wouldn't have an evenly spaced sequence of lobes like that, but could be chirped and in other ways could be tailored. I won't go through lots of technical detail in this talk, but one feature that is kind of important for the measurements that we make is that these time-dependent fields, either single cycle or multi-cycle oscillations or what have you, including the signals that we measure that emerge from samples, either as free induction decays or as echoes and other kinds of linear or nonlinear signals, we can actually measure the entire time dependence in a single laser shot. And the way that works is the following. All of these measurements are done using an electro-optic crystal, what's called electro-optic sampling. And all that means is because it's an electro-optic crystal, just like with the lithium niobate, when the terahertz field comes through that crystal, the electric field of it modulates the refractive index of the crystal, and an optical pulse can be used to measure the field strength and the phase too. That is, it's measuring the direction of the field as well. So normally the way that's done is there's a terahertz field that has some time dependence, like what I've illustrated, and a single optical pulse, which would be short in duration, shorter than what's sketched here. It would be short compared to this cycle. overlaps with it and measures the terahertz field at one particular point in the profile. And then the experiment would be repeated, and the optical pulse would be varied. Its relative timing compared to the terahertz field would be varied with a delay stage. So in successive measurements, the optical ultra short pulse would measure this little piece of the time-dependent terahertz field profile, then this one, then this one, then this one, then this one, point by point on the time axis, by gradually varying this delay stage and varying the time of arrival of the optical pulse. And usually there'd be signal averaging while all that's done. But an alternate method is we take the optical readout pulse and we hit this stair-step echelon structure. It's just nothing more than a stair-step reflector. So what comes off of this then, I haven't shown how the fact that the optical pulse is as big as this is. So different parts of the spatially large optical pulse arrive at different regions of this stair-step structure. And because of that, the reflected pulses go different path lengths. And because of that, they have different time delays. And so it's pretty straightforward to make on the order of 500 separate readout pulses. That is, this will not have this many ridges. It might have 500 separate steps that are, and the reflected pulses might be incremented by 20 or 40 or 50 picoseconds. So, and now they'll all go into this crystal and overlap with the terahertz field in it, all in one shot. So one of these will measure the terahertz field profile right here, the next one here, the next one here, the next one here, and so forth. And in the end, of course, what's happening is the electro-optic crystal is changing, its birefringence is being changed by the strength of the terahertz signal, the terahertz field. And so in the end, what happens is all of those pulses, after they go through, the polarization components are separated. And if it's just a single pulse, then they go to simply two single element detectors. But in this case, they're going across two lines of a camera. And so now the different parts of the camera are seeing the signals measured by all of these different pulses that are just spread out laterally in this direction, right? So in one laser shot, we make a measurement of about 500 time points of the terahertz field profile. And what's shown here are those measurements. This is the time domain measurement, and this is the Fourier transform. The solid and dashed curves are the standard method and the single shot method, and you can see they're basically yielding identical results. But the single shot measurement is just one shot. It's extremely fast, and because the signals can be on the camera can be downloaded at the rep rate of the laser amplifier that's used at about 1 kilohertz. We can even if we can still average if we want to, but even a single shot yields quite good data. But I mention this because in a number of measurements, for example, when we do two-dimensional terahertz spectroscopy, there are two time axes. There's a time axis, of course, the separation between 2 terahertz pulses, and that gets varied. And then there's the time-dependent signal field that needs to be measured. And if we use the sort of standard measurement method, then both of those time variables have to be swept one at a time, and it takes many hours. And this reduces that to minutes because now all the signal collection is done on every shot. So there's only one time variable, the time between different terahertz pulses, that has to be varied. Okay, now I just want to start illustrating some terahertz spectroscopy. And I'm not going to go through all of these. I'm not going to talk about dipoles, although they're also dear to my heart. I'll talk briefly about electrons, terahertz field action on electrons and ions, and then mostly about spins. And again, part of what I want to do here is just illustrate methodological possibilities that apply, regardless of what the nature of the measurement is. So some of the illustrations, some of the examples that I'll use here illustrate methods that would apply perfectly well to EPR as well. So let's start with electrons. So all I want to do here is just illustrate some of the things that terahertz fields can do as a result of driving electronic responses of materials of all sorts. So here's a case where it's just a dense coating of quantum dots, and the sample has gold strips with micron gaps between them, and they act like terahertz field enhancement structures, just like the dipole antenna, except instead of in one little region between the two arms of the dipole, now it's spread out laterally. So in everywhere between there's gold up here, there's gold up here, here's a couple of micron gap between them, and they're right around here everywhere. There's a strong enhancement of the terahertz field strength. And what's happening is the terahertz field is coming in, and it's just inducing charge transfer from one quantum dot to a neighbor, and then there's radiative recombination. That's all it is. So it's basically a kind of electroluminescence, although it's very different from electroluminescence that's driven by an ordinary DC or quasi-DC field. In that case, there's actually current moving from one electrode to the next, going through the sample. The terahertz field is just a single cycle that's on for 1 picosecond. Even over this couple of microns, there's not nearly enough time for current to flow from one electrode to the next. Rather, the field itself is inducing electron transfer from one dot to another dot in this region. And you can see also that although here you can see there's luminescence coming out from all of these micron gaps. It's actually not even strongest in the center of the gap. It's strong. It's more like fringe fields effects at the edges of the gold coatings. Here's one other example that I'll share. In this case, what's happened is the terahertz field has rearranged the charge distribution on this atomically thin molecular molybdenum ditelluride layer, and that has led to structural change that's permanent. So only one terahertz pulse ever irradiated the sample. This is the electron diffraction pattern of the sample originally. Here it is after just 1 terahertz pulse irradiated it, and you can see there's been cell doubling and so forth. So you can see the electron diffraction pattern is very different. And that's because the material has entered a different phase. It's actually a topological insulator phase that has been induced by the single terahertz pulse. And here's a more molecular type example. This is a kind of prototype for electrocatalysis in a general sense. This is really just a photoconductive circuit with organic moieties coated on top. And now optical light comes and makes electronic excited states in the molecules. But those are bound states, so there's not a lot of photocurrent that's generated that way until the terahertz pulse comes in. When the terahertz pulse comes in, basically it ionizes the electronic excited states, the excitons. That makes free carriers, and now there's photocurrent. So this is just an induced current measurement. The optical pulse is on all the time, but in this case, the terahertz pulse timing isn't done well. The terahertz pulse is arriving first, and it's over before the optical pulse comes in. So the terahertz field has no effect on the conductivity. But if the terahertz pulse comes after the optical pulse, now the excitons are there, and the terahertz pulse ionizes them. Interestingly, it actually ionizes more if it comes in while the optical pulse is in there. That's because the optical pulse makes hot carriers that live a short time before they relax into the exciton state. And now what I want to illustrate is maybe the most relevant to potential applications for basically time-resolved EPR. So what this is a kind of magnetospectroscopy where we first have an optical pulse that excites the sample, and all it's doing is making free carriers in silicon. The silicon is buried deep inside a magnet bore. So now they're going to be, lino levels. We're going to do basically electron cyclotron resonance. The terahertz field is going to come in and induce those resonances, and we're going to measure the terahertz response after that. So here's the magnet. A terahertz field and an optical pulse are both coming in here, and we can vary the timing between them. and we're going to measure the induced terahertz response, right? And we're going to make that measurement with that single shot approach that I illustrated. That's really important because this isn't straight 2D terahertz spectroscopy, but there are two time dimensions. There's the time between the optical pulse and the terahertz pulse, and then there's the essentially the free induction decay that the terahertz pulse induces. So we need to measure that field as a function of time as well. And that measurement, that latter measurement, is what we measure on a single shot basis. So here's typical data. These are the two time axes. The time between the optical pulse and the terahertz pulse, that can be varied over a few hundred picoseconds. It's just the lifetime of the carriers. On a shorter time scale is when the terahertz pulse comes in, it induces these oscillatory responses that reveal the electron cyclotron resonance frequencies. If we do that as a function of the magnetic field strength, this goes from about 3 to 9 Tesla. You can see that the frequency scales, it increases linearly with the field as you expect, and what these give us are the effective masses of the heavy and light and whole and the electrons. So we can measure them all in this manner. Okay, now I just want to illustrate briefly also what happens when we drive ions. This is also kind of relevant because for terahertz spectroscopy of many molecular materials, they're in crystalline form in many cases. So whether you intend to or not, you're likely to drive lattice responses as well as spins, right? But there's all sorts of interesting possibilities when that gets done. And in fact, using a fairly strong terahertz field, there's actually a small subfield that exists at this point in terahertz-induced phase transitions. I showed you one before where we induced the phase transition by basically changing the charge distribution. That is, the terahertz field was acting on electrons. Here, it's going to act on the ions, and it's going to move them right into the positions where they belong in a new phase. In this case, the new configuration is transient. It's not permanent like what I showed you before, but it just illustrates what's possible. So it's strontium titanate, and it's paraelectric. This has what's called a quantum paraelectric phase. It actually never goes ferroelectric, unlike many other members of this family, like lead titanate and many others. Strontium titanate actually doesn't have a ferroelectric phase. It approaches it. It looks like it's going to turn ferroelectric, but it never does. And that's because the potential minima away from the center for that ion are so shallow that even the 0-point vibrational energy is higher than those very shallow minima. And so there's the quantum uncertainties prevent any permanent long range ordering to make a well-defined ferroelectric domain. But that doesn't mean we can't, on a transient basis, push those ions in the way into the configurations that they would occupy in such a phase. And that's what we did here. And I'll just illustrate it briefly. You can just see that if we increment up the terahertz field strength, at first you just see how ordinary oscillations of this lattice vibrational mode of it's just the titanium ion rattling around inside its cage. But as we increase the field strength, suddenly, first of all, there's a marked jump in the strength, much more than would correspond to just the increment of the field strength. But more important, the time dependence itself is completely different. And you can see that in the Fourier transform. Suddenly, these new modes appear that didn't exist before. And what's happening is the lattice configuration isn't the same as it was at first. It's no longer that high symmetry configuration with the ion in the center. On average, the ion is off center. And now the lattice vibrations and the allowed transitions are different. So you can clearly see that things have changed considerably. We actually then went to the X-ray free electron laser facility at SLAC to measure this with X-rays, right? It's a remarkable thing. You can probe directly with X-rays. Part of why I want to illustrate this, though, is because it's also possible to do X-ray absorption and resonant X-ray scattering, where then the X-ray wavelength can be resonant with a core transition, and it's quite sensitive in that case to spins of a selected element, right? So there's actually a whole body of work where terahertz fields have excited samples, which have then been probed by resonant X-ray absorption or scattering. What I will illustrate isn't that, it's just X-ray diffraction or diffuse X-ray scattering, but that's also pretty illustrative. And so what happens is we come in with our terahertz field and suddenly we can see all these coupled lattice vibrations going because we've moved along one dimension, along one lattice coordinate quite far, but others are coupled to it. This lattice vibration isn't the soft mode that we're directly driving with the terahertz field. It's coupled to it. So its oscillations also follow the terahertz pulse. And maybe more surprisingly, when we actually looked at essentially the soft mode type vibrations, what we saw is we certainly saw that oscillation, but in fact, it's not at a Bragg peak, it's off Bragg. And that's really quite striking. What it's saying is, although in our optical measurements, we thought we were inducing a completely spatially uniform transient ferroelectric configuration, what this is showing us is really what we're inducing is that configuration in much more strongly induced in pre-existing polar nano regions on the order of 10 nanometers, because there's spatial structure there that's pre-existing prior to our excitation. It's just a really striking result. All right, now I want to illustrate. Now let's get to spins and terahertz EPR. So let me start with the small amount of work that we've done on molecular systems. This really was just illustrative, and I still do hope to do much more. But here are just examples where we're looking at high spin transition metal complexes, looking at zero field splitting transitions, right? And so here's one example. It's this Hymen, and you can see these free induction decays are given. If we Fourier transform them, we just get the terahertz, the EPR spectrum, the couple of peaks that are characteristic of this. And what we did is just walk through a number of different high spin complexes. So here the spin is 2, 3 halves, 1, a couple of different examples of each, and in each one in 3 halves, and just showed that in all of these cases it was actually pretty straightforward to record the terahertz EPR spectra. Really, it was pretty straightforward to do. And this, by the way, was before we had introduced this single shot measurement method. These would be far quicker and easier now than they were back when we did these measurements a number of years ago. But where we've really focused our efforts aren't on molecular systems, but collective spin waves or magnon modes. And what we've studied are crystalline systems that are nominally anti-ferromagnetic. That is, they have two magnetic sublattices that are opposed to each other, but there's an interaction between them that leads to a canting of the sublattices. So there's a small net magnetic moment. And then there are modes of collective spin modes that deviate from that equilibrium, either through precession of that moment or by variation of its amplitude. What's really happening is that the sublattices are either in or out of phase to give rise to these two magnon modes. And these are driven by terahertz magnetic fields with different polarizations. This precessional mode is driven by a terahertz field in this direction. It takes the magnetization and it drives it this way, and then precession ensues. This amplitude variation, this quasi anti-ferromagnetic mode, called a quasi ferromagnetic mode, the lower one. This one is driven by a terahertz field that's in the direction of the magnetization, and it induces oscillations of the magnetization amplitude. These are just linear spectra. These are just free induction decays recorded with the two different terahertz incident polarizations, and these are their Fourier transforms. So we have two magnon modes at sub-terahertz frequencies at about 0.3 and about 0.57 terahertz. These are two-dimensional, or this is a two-dimensional spectrum. This is a simulation of it, of the anti-ferromagnetic mode, that is this amplitude mode, because it was taken with the terahertz polarization aligned with the magnetization axis. But the important point is that you see rephasing or spin echo, non-rephasing, and two quantum peaks, right? That is, you see all the expected third order nonlinear signals that should show up in a two-dimensional spectrum. You also see pump probe signal as well, and even rectification of the Terrace field and second harmonic generation. That is, you see second order signals as well. This was all done back again before we had developed that single shot measurement method. So these actually, each of the two-dimensional spectrum like this took a couple of days to collect, because again, like I mentioned, we're setting the time between the two terahertz pulses that were used, and then we're recording the terahertz nonlinear signal field. Then we're incrementing that time between the two terahertz pulses and incrementing the signal and measuring the signal field again and so forth each time, signal averaging pretty extensively. So it takes a long time to take a 2D spectrum of this sort, right? But here's what happens now we've got the same single shot detection approach that I showed before. That is, here's that stair step echelon structure, and now there's a CMOS camera recording the two different polarizations for each of about 500 pulses. I won't go into great detail, but these nonlinear measurements are all done, but with chopping of the readout pulse of each of the two incident terahertz pulses, so that we can subtract away the signals that aren't arising from the presence of all of those pulses. So here is just an illustration of the benefits of the single shot detection method. Here's the spectrum that I showed you. This took about 3 days to collect. This is minutes, and we're better at this now. In fact, we rarely take a half hour for a 2D spectrum. So it just completely changed what we were able to do, because of course, what it really means is we can make far more systematic studies of interesting materials. And here's an illustration of that. These are 2D spectra, and now it's 2D terahertz polarimetry. That is, we've got our incident pulse pair with a certain polarization, and in this case, we're detecting the coherent signal either parallel or perpendicular to the polarizations of these two. And what I'm going to show you here are 2D spectra recorded just by taking the crystal orientation and rotating it in 5-degree steps. So that's 72 spectra in each of these polarization configurations, or 144 2D spectra, and all of them were taken in less than 1 day. It took about 22 hours to record every spectrum. I'm not belaboring every one, but the point is, suddenly it becomes possible to do systematic study like this, right? Which just would have been inconceivable before. This would have been the work of years using conventional detection. So here are some of the things that were learned. So it's two-dimensional spectroscopy, and of course the really signature capability of any kind of 2D spectroscopy is the unveiling of correlations between transitions and coupling between different modes. So here's a case where when we have the incident polarizations at 45 degrees, so each one of these incident pulses is going to drive both modes. Suddenly we see sum and difference frequencies of those modes. Those sum frequencies, those are two quantum coherences. In other words, there was an initial transition that made a coherence in one of the Magnon modes, and now a second transition made a coherence in the other, but they're not just independently oscillating. Of course, they are. We do have signals like that, but we see a signal at the sum frequencies, right? And what that's saying is that you actually have nonlinear coupling between the modes. They know about each other. Of course, their magnetic moments are interacting with each other. So there's a correlation that results in these nonlinear sum and difference frequencies, right? So we also have harmonics and rectification. So here's a harmonic of each of the incident frequencies. But more interesting in some respect is the coupling between them that's illustrated here. Here's another thing that we didn't anticipate, but is quite understandable once we figured out what we were seeing. This was done in the following way. The incident pulses were both polarized in the direction that would drive this precessional mode. Right? So there shouldn't be any signal in the direction of the amplitude mode, the other mode. But there is. And that's what this off-diagonal term is coming from. And it's only present if we drive the precessional mode and detect the other mode. If we drive the other mode and look in the direction of the precessional mode, we don't see anything. In other words, there's a nonlinear coupling here, but it only goes in one direction. And it's actually not hard to understand. What's happening is that when we drive that precessional mode, we are necessarily reducing the magnetization component along the original direction. And that means we must always be coupling to the amplitude mode because we're changing the magnetization magnitude in that direction. Right? That's what's happening. This problem actually maps exactly onto the model of a pendulum that's also a spring. So if I just knock the spring down and make it stretch, that's all that happens. But if I hit it this way and start it moving as a pendulum, of course, it also stretches. In other words, here too, the nonlinear coupling is only in one direction, not in the other, right? But mathematically, the problem maps, the two problems are completely conformal. They map exactly onto each other, right? It turns out there actually is another mechanism that can produce this same off-diagonal peak, and it's the following. If when I have a first field interaction, so I'm driving the system with two pulses in this direction, and I'm driving it nonlinearly. The first field interaction starts the precession going. This field in this direction shouldn't couple to the amplitude mode. But once I already drive precession, I've broken the symmetry. So now there is weak coupling between the second field that's polarized in this direction and the amplitude mode, which is no longer exactly orthogonal. So that also can produce these signals. But they have very different behaviors. And in particular, the mechanism that I described before, this nonlinear coupling between the modes, as opposed to just the field itself driving both modes. The nonlinear coupling is optimized when the mode frequencies are in a 2-to-1 ratio. And the frequency of one of those modes is quite strongly temperature dependent. So we can vary the temperature until we reach the point where the two frequencies are in about a 2-to-1 ratio at about 200, a little more than 200 Kelvin. And sure enough, there's a strong peak in the signal there from that component. But there is signal elsewhere always. And in fact, in general, both of those mechanisms do contribute to the signal. Finally, we see one additional parametric amplification signal. And that means if I drive the higher frequency mode and then drive the lower frequency mode, I get amplification of signal at the difference frequency, right? It's real parametric amplification based on coupling, nonlinear coupling between the magnon modes. And it's quite striking, and it has a strong peak also at 200 Kelvin because it too is optimized when the frequencies are in the 2-to-1 ratio, because then when I drive that second lower frequency mode, I'm also resonant with the final emitted signal. But this is completely different from before. In the earlier example that I showed you, the incident polarizations were along the direction of the precessional mode only, right? Here, I'm driving both of the modes with polarizations that enable that, right? So it's what the polarization conditions here are very different from what I described before. This is parametric amplification, not that kind of one-way nonlinear coupling. So what I've tried to just illustrate different kinds of features that can be revealed by these 2D spectroscopy measurements. Of course, I'm quite keen on generalizing these to molecular systems as well, where, for example, systems like multinuclear, either biomolecules or just multinuclear transition metal complexes, for example, where there'll be interactions between spins on different ions that could be important in a lot of ways. But I'll just go a little further and show what happens if we do the same measurements, the same sort of measurements that I illustrated before, but with considerably stronger Territz fields. So here is another Territz field enhancement structure, but it's not a deposited structure on the surface of something. So this is really just a metallic waveguide with tapered entrances, and it's literally just essentially just sort of compressing the field inside it. So both the electric and magnetic fields are increased substantially, right? And this has the advantage that it actually has a small volume, a small but macroscopic volume of material can go in there. And we literally put one of these same canted antiferromagnetic crystals in there. These are orthoferrite crystals, yttrium and erbium and others. And here's what happens. Suddenly, now what we're seeing is 2D spectra. But remember, I mentioned there were multiple quantum peaks. Now this is just one of the modes, right? It's the precessional mode. But now we're not just seeing two quantum coherences. That's what would happen, when we see up here, for example. So in a two quantum coherence, right, the first field, it produces a coherence, and the second field goes up to the next level, and that in most cases doesn't radiate. But now, so the first pulse will interact twice to do that. And the second pulse comes in later, and it's going to project back down to a single quantum coherence that does radiate. But as you vary the time between the two pulses, that second Territz field is interfering with the two quantum coherence. So that final single quantum radiative coherence, its amplitude oscillates at twice the frequency, because that second pulse, its field that's bringing the coherence back down, is interfering with this two quantum coherence at 2 omega. So that's why on the excitation axis we have the signal at twice the frequency, right? But here's 3 times, here's 4 times, here's 5 times, 6 times, here's 7 times. So now what's happening is this: it's still only 2 pulses, but they're much stronger. So now the first pulse is interacting with the sample up to 7 times to make a 7 quantum coherence. It's actually tilting that magnetization axis by about 30 degrees. So it's really driving it far. That high order coherence doesn't radiate. That requires 6 more interactions in the second pulse to bring it back down to a single quantum coherence that radiates. And it does, and that's what makes this signal, where when we vary that second pulse, the radiation that we measure as a function of its delay, it oscillates at 7 times the Magnon frequency. And there's a component at 6 times and at 5 times and so forth, because it's bringing back down the 2, 3, 4, 5, 6, 7 quantum coherence all the way down to a single quantum coherence, which is what finally radiates the signal that we measure. So the point is that we can actually control the magnetization to a substantial extent, and there are already examples where Territz magnetic fields have switched domains, right? So, this is what the rest of all of you would say, well, yeah, sure, that's just a pi pulse, right? But of course, it's a little bit different from your garden variety pi pulse, or in some cases pi over 2 pulse, because of course you really are taking a net macroscopic magnetization and switching it. in the cases studied so far, it didn't stay there. But I think there's every reason to expect that that will happen, and I'm quite optimistic that it'll happen fairly soon. That is, we should be able to do real coherent control over the magnetization state of crystals like this, right? And of course, there's a whole wealth of possibilities that opens up then. Okay. By the way, this nonlinear spectroscopy involved the whole group of people, including a group that made the crystals, some folks that helped with the theoretical modeling, and then the people in my group who did the experiments and a lot of the modeling as well. So finally, I want to end with how we can do these kind of measurements without ever having any free space terahertz propagation. What I've showed you so far, all of that was done with free space terahertz fields. Let's change that. So I'm going to show you one more movie of terahertz fields propagating. This is in a 50 micron thick crystal. And again, a line of light excited it. But in this crystal, there are waveguide, there's dispersion. And so what you're going to see when these things reflect back and interact with each other, they'll interfere with each other. And you can see the interference fringe spacing getting shorter and shorter as time goes on, because the shorter wavelength components traveled slower than the faster ones. It took them longer to find each other and overlap with each other. So there's dispersion that we measure that way. And there's also more than one waveguide mode. So if we just take what I just showed you and Fourier transform it in both dimensions, we immediately get the full waveguide dispersion properties of the different modes. Okay, so we're Fourier transforming with respect to frequency and with respect to time and position, and we get frequency and wave vector. Okay, in other words, we get the waveguide dispersion. That's fine. Now I want to not just have a lithium niobate 50 micron thick planar waveguide. Now I want to take one of these orthoferrites and I want to just stick it on top. And I want to make a hybrid waveguide that consists of the two. So now it's going to be about 100 microns thick. Still is a terahertz waveguide. But now it has these two components, one of which hosts these magnon modes. And so when we excite the terahertz field, the electric field is in all the illustrations I've shown you so far, and in this one too. The electric field is polarized in the plane. And it's interacting, like I mentioned, with the niobium ions and the lithium niobate. It's actually making phonon polaritons. And so, in other words, there are lattice vibrations that are oscillating along with the electric field. But the magnetic field is in this direction, and it's going to drive the magnon modes, whichever one happens to be, depends on the crystal cup. It'll be aligned with one of those two modes or with both, depending on the cup, right? So now we're going to make magnon polaritons this way. So we're going to, in this case, we actually had the lithium niobate slab stick out a little bit, and we excited it directly, and then excited the waves and probed them. And you can see, let me just go to the results. So this is the dispersion that I showed you just a minute ago. This is just a bare lithium niobate slab. This is the hybrid lithium niobate and erbium orthoferrite. And it doesn't look that different. But what's going on right here? Let's look a little closer. If we do that, what we see is that, in fact, so this dashed line is just the normal magnon frequency. It shouldn't have any dispersion. But and this is the dispersive terahertz frequency as a function of wave vector, right? As the wavelength changes, of course, the frequency changes. It's a phonon polariton mode, but really it's just basically acting like terahertz light in the lithium niobate. But because the terahertz magnetic field couples strongly to the magnon mode, there's an avoided crossing here, and magnon polariton branches are formed, right, in both of these terahertz waveguide modes. So what that's showing is in this coupled waveguide structure, we actually are in the regime of strong light matter interactions, where you have splitting of the modes into upper and lower polariton branches, right? So what we've done is basically record essentially the Terrett's EPR spectrum to reveal that in fact we have strong light matter coupling here, right? This is just linear spectroscopy, by the way. This isn't strong field stuff, right? But the point is the nature of the modes is influenced by the fact that inherently there is strong coupling between the Terrett's magnetic field and the magnon modes. We also made cavities where photonic band gap cavities, what we did is just laser machine a bunch of holes right through, not this is just lithium niobate, and you can see it's acting as a photonic band gap structure, reflecting some frequency components and transmitting others. But we did this for the hybrid waveguide too. We just machined all the way through to make, and then we didn't make holes here, so that there's basically a defect cavity in the structure. And when we did that, now there's no wave vector we can vary, right? Because we have a cavity like this. But luckily, both the magnon and phonon frequencies have a weak temperature dependence, and they cross. And if we vary the temperature to where they cross, we see that actually they avoid crossing, just like we saw before as a function of wave vector. In other words, in these cavities, there's also the very same strong coupling between the magnon mode and the Terrett's magnetic field that leads to the avoided crossing, right? So we've made all sorts of cavities. This is the one I illustrated for you before. What I showed you is actually a little bit neater when we use a cavity like this. But the point is, we actually can fabricate all kinds of structures, and we're in the process of doing that to facilitate a whole set of 2D and nonlinear spectroscopy measurements. So I want to just finish with one example of that. Everything I've shown you so far has our optical light. You know, if this is the terahertz crystal, the optical light is coming at it and going straight through. The terahertz waveguide is about 50 microns thick, and the light just goes through, and that's it. It's not a very effective way to pump because, of course, almost all the light is still there. Very little energy has been imparted to produce these coherent terahertz waves. It's a little bit better when we pump a bulk crystal like I showed you before, because at least then there's an interaction length that's longer than 50 microns. But here that's all there is, because that's as thick as the material is. Unless we bring the pump pulses in from the side of the thin slab. Then they can propagate in the plane of the slab, and that's a long distance. And as they propagate, they'll build up a field. Now, remember I mentioned that the refractive indices are really different. So if we just do that, it really won't work very well, because the light comes through way faster than the Terrett's field can follow it. But if we start shaving down the thickness of the Terrett's slab, then more of the Terrett's field is the evanescent field in the air, and that reduces the refractive index until it can match the refractive index of the pumping pulse. So we did that. That happens at about 30 microns or so. It can be controlled. Now the Terrett's pulse, the optical pulse comes in and is continually driving a Terrett's field. However, the group velocities then don't really match perfectly. So it'll drive one lobe for a while, then slip off to the next lobe, and it'll make multiple lobes, but none of them is very strong. So what we did instead is use a whole optical pulse sequence. So then every lobe is driven all the way through. And that makes really high spectral brightness, better than we get with bulk generation. So here's what happens. Here's the refractive index for light. It's a little bigger than 2. The refractive index for the terahertz field, this is the dispersion. And if we change, depending on the thickness, we can control where it crosses the light. So we can select a particular terahertz frequency that we want to drive this way. And here's the result. So now we came in with side pumping like this and built up lots of pulses, making a somewhat narrow bandwidth, but this was just with one incident light pulse. Instead, now we came in with a whole sequence of optical pulses made by multiple reflections. So now we come in with this incident train of pulses, and we get a much stronger amplified field and a narrower line width. So this is about 30 gigahertz, but actually we've just recently reduced this to just about 3 gigahertz using, we doubled the number of pulses. So we can get quite narrow band multi-cycle fields. Now, what we call narrow band, of course, I think in the world that most of you live in, that's still broadband. I went through a number of talks that Yuji sent me of previous speakers, and I think Yuji herself in her talk said, well, we make a field that says it's got a bandwidth as large as 3 gigahertz. We've succeeded in making a bandwidth as small as 3 gigahertz. for us, that's narrow band by our usual standards. But interestingly, in these fields, the spectral brightness is pretty high. So let's see that. That's illustrated right here. Here's the spectral amplitude of our single cycle pulse generated in a bulk crystal with about 10 microjoules or with about 10 millijoules of optical pump light. And here's the spectral brightness of a multi-cycle field, not even our narrowest one, generated with only 2 millijoules total of pump light. And it's brighter, which means for a narrow resonance, it can pump it harder. And those magnon modes are pretty narrow. So here is our first 2D spectrum of this magnon mode taken in this form. So again, here's lithium niobate. Here's yttrium orthoferrite just laying right on top of it. Literally, we stick these things together with nail polish. There is no fancy fabrication at all. And we now measure the nonlinear signal, and there it is. So the point is we can do not just linear, but also nonlinear spectroscopy with no free space terahertz propagation at all. Right? All of these examples are are with the magnon modes in these canted antiferromagnetic crystals. I'm very keen on, instead of that, and there are various interaction geometries. We could have a divot in here and have a powder sample in there. There are lots of ways we can have these incident terahertz fields interact with a sample. But the point is, even with the sample deep inside the magnet bore, there's no corrugated waveguide, there's no nothing. There's just a nice little optical laser beam going into the magnet bore to generate the terahertz field itself right there in situ. The terahertz field interacts with the sample while it's still in the waveguide. And we measure the terahertz field, the terahertz signal field, while it's also still in the waveguide. So there's no free space propagation anywhere of terahertz light. Right? And that's what we're trying to now move farther so that we can really do the full range of spectroscopies that we would like to do in this way. Right? These are images of terahertz fields that are both incident in one crystal. So the crystal is a planar crystal like this. Here's one terahertz field, here's another. This is a deposited gold structure that's going to focus and reflect the two and cross them. And that's what you can see happening here. Here's where they cross, and that's where nonlinear stuff happens, right? In this case, actually, even in the lithium niobate, we saw some indifference frequencies when we put in 2 different frequencies that way. So I just want to sort of summarize. What I've tried to show is that we can do various sorts of terahertz EPR. I showed almost everything I showed was done in free space. And it's well suited for samples like these high spin transition metal compounds or these magnon modes. And I showed at the end that this is possible without any free space terahertz propagation. Here's what I didn't show. I didn't show any Zeeman EPR. Here's one of the reasons why. everything I showed you was done on really, by any standard that I think you're probably used to thinking, very fast timescales, right? Tens of picoseconds. Right? Sometimes we've gone out to hundreds of picoseconds. That's about as long as we've gone, right? And that's fine for modes like these where the dephasing times are pretty fast and we can do all of the measurements that we need to do on those timescales. Obviously, that's not the case with just ordinary Zeeman EPR with very narrow lines that go out microseconds, right? So how do we do it? Well, any of these pulses that we're generating are coming from a mode lock laser. It puts out a pulse every 12 nanoseconds forever. So we could use any of those to make terahertz light that would probe. So I do think we could do things like make free induction decay measurements out to arbitrarily long times in various ways. What isn't quite as easy is to make multiple pump pulses that are strong, right? Because an amplified laser produces one such pulse. The oscillator before the amplifier produces pulses every 12 nanoseconds, but not strong pulses. They're fun. They could be used as probes, but not for nonlinear spectroscopy pumping pulses. It's possible to sync the outputs of more than one amplifier. We do that on one of our existing systems. So yes, we could have at least two pulses with long delays, arbitrary delays between them. And potentially more, but that's expensive to have multiple amplifiers and so forth. So what I'm hoping is to engage some of you in formulating what might be the optimal conditions for some measurements that are tailored to measure some of the things that would be most interesting, right? And since all of our work really has been aimed at collective modes of the kinds that I've been illustrating, I'm interested in talking with anybody out there who's interested about what are some of the potentially exciting molecular measurements that could be made here. Some that might not require very long time scales could involve time-dependent EPR, where there's photoexcitation of a species that has evolution on fairly fast time scales, right? And that's a delay that could be made arbitrarily quite long anyway, because it's a delay between an optical pump and a terahertz probe. It's a little trickier to make long delays between multiple terahertz pump pulses. Now we do it just with mechanical delays, but of course that only can go out to whatever, 10, 20 nanoseconds, that kind of time, not to hundreds of nanoseconds or to microseconds, right? For that, we need at least two amplifiers. I'm hoping to get that, but the point is it's not trivial. So that's where we are. And I'll leave it at that and acknowledge the terrific people who, these are not the collaborators that I tried to acknowledge before, but these are the folks in the group who have really pushed all of this further. Eduardo was a collaborator, actually. Baldini, the last fellow, he's now a faculty member at UT Austin. And the others have really moved things forward. The very first person listed, Zhupan Zhang, recently graduated and is now a postdoc at Columbia and led a lot of this nonlinear spectroscopy work. Thanks a bunch.
Thank you very much, Keith, for the interesting talk. So we're a little bit behind the schedule, so we will do a mini Q&A.
Yeah, sorry.
Anyone have a question, so feel free to unmute yourself and raise your hand or just text in the chat box. So I will start with a very naive question. Would it be interesting if you combine the terahertz pump and the conventional EPR? So you use a terahertz pump pulse, and then you introduce some population redistribution, and then you use some microwave pulses to selectively observe how the population changes between different transitions and so on.
I suppose it depends on what your magnetic field strength is, right? In most of the cases that I'm envisioning, our terahertz pulse is resonant with a transition. So even if it's Zeeman, that means the field might be 9 Tesla or something, right? So in that case, I suppose that approach wouldn't work. If the Terrace field instead is doing something different, right? Of course, if it's changing a charge distribution, if it's basically acting as a pump pulse for whatever degrees of freedom, a little bit like the case of the optical pulse that I illustrated before. Well, then, of course, for sure, you could probe with conventional or EPR methods.
Yeah. I guess it won't work for many samples, but if there are samples happen to have the Zeeman transition at the right field, at the right frequency, so maybe that's something you could.
Well, no, but I mean, of course, we can always adjust the field or to make that possible, right?
Yeah.
But what I'm saying is that if we have done that so that our terahertz field is already driving the sample, which means that the frequency is up maybe 300 gigahertz, something like that, if we're at about 9 Tesla, then if your idea is to then bring in microwaves as the next step, whose frequency doesn't match that, well, then of course it won't be able to resonantly drive or probe the same response, right?
Yeah.
What might still be useful is, of course, you and others, and I've seen a couple of the previous talks that certainly did make measurements up at the same frequency ranges and same magnetic field strengths, and it could turn out that it would be useful to use some of those measurement methods, right? Even if we generate the pump pulse, and I say that because that might mean then that you would have a heterodyne field for the a reference field for the signal to mix with and so forth, right?
Yeah. Right. Is there any other questions? And the other one I had in mind is so what in your opinion, what is the main difference between having the pulse up converted from microwave to sub-terahertz frequency and using the optical source to kind of using the nonlinear component to get the sub-terahertz frequency? So what is
well, there's several differences. Obviously, one is that of course the pulse duration can be extremely short. Typically, of course, it is very short. It's all the way down to single cycle. What that means is if you want to do something like a broadband spectrum of zero field splittings, right, multiple transitions, right, that's what we did in those molecular examples that I showed at first. All those were done by just bringing in a single pulse whose bandwidth was big enough to include all the transition frequencies. And in fact, broader bandwidths are even possible, right? Mm-hmm. Similarly, of course, if you wanted to do time resolved measurements with fairly high time resolution, then of course it's favorable to generate the Terahertz fields this way, right? I'm not sure. I'm looking at what would be the possible benefits or limitations of adapting what we're doing to more standard Zeeman EPR measurements, right?
Yeah.
If it's free induction decays, well, I'm sure we could do that, right? But and of course, if the frequency is high, maybe that's more facile. I don't know. Then you don't need a very strong field, so you can probably use harmonic generation and get up to a very high frequency and not worry about it, right? It might start to get different depending on how strong you want the field to be, right? If you need multiple pulses and so forth. Right?
Yeah.
Yeah.
Right. Given we are a bit late, so we'll finish here. And if, as a EPR user, you have any ideas about how this technique might be adapted for your application, so feel free to contact Keith as well. Let's thank Keith again for the nice presentation, and I will see you in a few days. Thank you.
Thank you. Bye-bye.